Welcome back from break. We're going to continue the session with a very interesting talk, in my opinion, that will take us into some application domains. Our speaker is Dr. Satyajit Mojumdar. He is an assistant professor here at WSU with the School of Mechanical and Materials Engineering. And he works in an area that is fascinating, additive manufacturing and advanced manufacturing. He will probably spell the differences between them out for us. But I have known Jeet, that's the shorter version of his name, very recently, and we collaborated on a project. And I invited him to speak at this workshop, and he was very willing to do that. And he will probably tell us a little bit about his lab. For those of you who are in computer science and look for applications where you can use your cybersecurity and other skills in a good way, I think further interactions with him would be a great opportunity. He will probably tell us more about those sort of things. And so please join me in welcoming Jeet. That's right, yes.
Thank you, Asafo, for introducing, and thanks for being here on Friday. I understand it's difficult for you to, this is the 5th day of your program, so it's probably very tiring, but I'll try to keep you engaged in this presentation. So I'd like to start with a question. So in terms of cyber vulnerability, which industry do you think is the second most vulnerable industry in cybersecurity aspect?
Automobiles.
Advanced manufacturing.
What's that?
So I'll give you 3 options maybe, just to give you a context. So healthcare, finance, and obviously I'm talking about advanced manufacturing. So manufacturing. So what do you think is the second most vulnerable industry? Who about finance? 1, healthcare. 1, 2, manufacturing. Most of you? Okay. So I successfully convinced you to answer the wrong answer. That's what a hacker does, right? So manufacturing actually the top industry, which is vulnerable to cyber attack. And I'll show you different instances and example in this lecture. So what we'll cover today? So I'll give you a little bit primer on the advanced manufacturing. So as Dr. Asfa said, like the difference between advanced manufacturing and additive manufacturing is probably not very clear. You have heard probably both of these terms. So I'll try to distinguish these two and then going into a deep dive into additive manufacturing system and what are the different attack surface for this system. And then you'll be able to learn a little bit more about that. And then I'll cover a little bit on the other advanced manufacturing domain, but we'll not have time to go into the deeper side of it. But if you're interested, we can talk later. The next topic. Okay, let us fix this.
Yeah, it's good.
Yeah. Okay, sorry. Then we'll talk a little bit about the already existing defensive framework and the mitigation strategies that people use in this manufacturing industries. And lastly, I'll talk about some research frontier, like what are the key research aspects in this topic. So the goal here is to give you an understanding of the attack surface for the modern manufacturing and give you a little bit more into the additive manufacturing aspect of it and look at different kind of mitigation framework that we have already in this system. So advanced manufacturing. So let me ask another question again. So what do you think is the most oldest manufacturing technologies in Earth? Yes. Assembly line. Okay. How long assembly lines are there? Probably 100 years. Back to industrial age, but I'm talking about more than that. Any other guess? So the most oldest one is the stone cutting tool that dates back to probably 300,000 BCE. And then from there, people learn to use heat, and then they used to do the heating for some material to put it in a different form. That is probably back in 100,000 BCE. And most recent, like if you go through different kind of excavation, you will see some pottery coming out, right? So that is one of the most latest one, which is again 25,000 years old technology in the manufacturing aspect. And then you probably heard of metal technologies like joining and all these different kind of things. People have tried it around 10,000 BCE before. And probably, as you are saying about the manufacturing line, so you're familiar with probably the lathe machine, if you have seen one, that is still 1,300 years old technology. So you can see like the manufacturing technology is evolving, and we're going from traditional manufacturing and what we call now advanced manufacturing, right? So what advanced manufacturing is, basically differentiate between the traditional is this. So in the traditional manufacturing, so now take it back to your 100 years back technology. So you'll probably have a workstation like this. You'll have a worker, and then that worker will probably be working alone, getting data, doing some stuff, and then basically doing the manufacturing processes. Now, with advanced manufacturing, the system looks like this. Now he is no longer doing the part design from his intuition. He is using a CAD or CAM, which is computer-aided design and computer-aided manufacturing concept to design that part itself. Then we also have different kind of machine and sensor controller communicating with each other, which is a significant difference between the traditional manufacturing. In traditional manufacturing, your single unit is completely isolated, right? Then another key enabling technologies we have is industrial Internet of Things, cloud manufacturing, digital twin, and obviously with now this AI ML hype, we have this AI ML driven quality control. So these are all coming together under this advanced manufacturing hood. So the key paradigm shift right now is the machines right now are not isolated. They are connected with each other and they are talking to each other. Okay, so that is the key difference between the traditional manufacturing and the advanced manufacturing system that we have right now. So before I go into the little bit more details on the advanced manufacturing, I want to talk about these two concepts. One is operational technology, OT, and information technology or IT. I'm sure you are very familiar with the IT stuff as your computer science background. In the operational technology network side, you have basically different kind of PLC, sensors, machines. So you can think of those as the physical setup. For example, the PLC is basically a controller that controls your machine. So think of a heating system in your home. So there are many blower, fan, heating system, cooling system involved in that. And someone is controlling those, right? So that can be a PLC controller itself, right? So that's basically the operational technology network. And we also have the IT network. So before the industry 4.0, these two are kind of disconnected. So you can see that gap between these two technologies over there. But after industry 4.0, now these two are coming in a convergence zone. So now you want to control your heating system from your phone, right? So you see now, right now we have this kind of remote access, different kind of IoT gateway, so and different kind of networking system coming together that basically merging this information technology and operational technology together, right? So basically, if you have operational technology is something you probably don't have much control from the attacking aspect, but you probably have better opportunity to control the IT aspect. So if you have a compromised IT account, then you can basically lead it through the OT and can look into the system or go into the system to manipulate it, right? So that is the key aspect. So the critical insight we have here is when the OT, the operational technology is compromised, you will have problem with the safety, security of your system, and that is very critical. So you need to look into this convergence zone very carefully and design it so that we don't have access to everything is exposed, or you cannot basically access to the OT network through the IT network, right? And how you can design this convergence zone in a better way that is more secured, right? That is the goal here. So different kind of advanced manufacturing technology landscape, as I said, there's a difference between additive, and advanced manufacturing. So this slide probably will make it clear to you. So how many of you have a 3D printer or have used a 3D printer before? Most of you, okay. So I'm sure that if you have one in your home, that's probably a polymer 3D printer. Just you do some rapid prototyping, maybe $1,000 in that range. Maybe if you are having a higher end, maybe $5,000. So that's basically for printing polymer or doing some rapid prototyping. But if you look into the metal additive manufacturing, the machines are like 500K to 1 million, right? So, and then control system and everything would be much, much complex in that aspect. So what additive manufacturing does is it's basically deposit material layer by layer. So over a long time, our production process was you make a mold and then you make a part out of it, and that's it. You did some manufacturing, right? You can do some post-processing, maybe some CNC, maybe some milling, those kind of operation to get a final product. But it is very much fixed, like how the product is going to look like, okay? With the additive manufacturing, now you are building the material from scratch. So you're basically depositing material layer by layer. That gives you flexibility to design very complex part. You can now design very complex that people cannot do it with a mold, right? And another aspect is that now you can think of customized product. So if you just think of a mold, making a mold itself will probably cost you $1 million. And then from there, you can make many times, and that makes the product cheaper, right? But using additive manufacturing, you can maybe just make one part out of it, which is still not that costly, okay? So that is the main advantage of additive manufacturing, that you can make customized and personalized product out of it, okay? And we have seen application in different fields. One of the application area is biomedical implant. So you can think of if your hip implant is broken, I don't want that, but let's say hip is broken somehow, you need to replace it with the implant. Now for each person, it will be very different, right? Not everyone's hip is going to look similar. So if you do traditional manufacturing, it's not gonna work. On the other hand, if you do additive manufacturing, you can basically design your hip, just what you have from a CT scan or 3D scan of your hip, and can design and print it and then put it in your body. So that is the idea of additive manufacturing here. Then we have this CNC machining and robotics, which is another important aspect, especially for industrial manufacturing. So CNC means computer numerical control. So let's say you want to make a part, and that part actually have multiple things, maybe a hole, maybe a thread, maybe something else, right? Different kind of feature. So you need different kind of tool to work together in a metal piece to create that shape, complex shape, okay? So using this computer numerical control machining, you can basically give the command, okay, let's run a mill, let's run a something else, some other tools, and then you come up with a part. That's why robotics can also help. So robotics not only help you to take a part and put it in a different place. You have seen probably industrial robot where they're welding, they're inspecting stuff, right? So all these are kind of application of robotics in advanced manufacturing. Then another key aspect is digital twin. So when we talk about digital twin, there is also a physical twin of it, right? So you can see in this picture, we have a physical rocket engine, and on the right, there is a digital twin of that rocket engine. So the goal is that if you have a physical twin, you want to update that in real time with the digital twin, so you can predict what is going to happen, okay? And then basically based on the digital twin, you can make decision like, okay, is this engine safe to fly or not, right? So that kind of thing, we can do it under digital twin. And there are a lot of, not only manufacturing process, there are a lot of simulation, a lot of modeling, those kind of things are involved. But the key aspect here is that you have to pass the information from digital to physical and physical to digital. So there is the information transfer between these two domains. The last one is smart factories and industrial Internet of Things. So as I said earlier, factories right now are not isolated. So you have many machines, those machines are connected. We are using lots of sensor nowadays to look at the machining and the real time and then make a decision out of it. So all these machines are now connected. That requires new type of technique, new type of technology to maintain them, okay? So that's the smart factories and IoT aspect of it. So I already give you the answer. So if you are interested to look at some other industry that has the vulnerabilities, and this is from 2025. I think right now this is last couple of years in a row that manufacturing is the top field for cyber attacks. Okay, and I'll give you some real example. So one event happened in 2017. It's called Stuxnet. So what happened that there is a ransomware attack to Iran nuclear facilities, and that basically turned off all the turbo machinery over there. So that has a huge impact over there. And there is also another Norsk Hydro, a aluminum industry in Norway. So they also got this ransomware attack, and they have multiple unit in multiple different country, and all of them has to be shut down, and that cost them around $70 million. So what happened is that actually attacked the PLC for the system, and that stopped working. So here are few recent events. So one is 2025, and this is in Taiwan. It's on semiconductor industry, Unimicron. So one ransomware attack happened, and that disrupted the whole operation. And Nucor one is on the United States, and that is a steel production industry. And then similar ransomware attack happened, and then it halted the whole operation for that one. So you can see that there is a real consequence. And when you talk about this level of attack, we're talking in terms of billions of dollars, because if your industry is halted for one day, you are losing money. Okay, so this is very important, and not only important from the monetary point of view, there is also safety aspect. I'll talk about that aspect later, like why that is very important. So giving you a little bit now detail on the additive manufacturing aspect. So what you are seeing here on the right is the additive manufacturing process, and we call this directed energy deposition. You can see material is deposited layer by layer, and you are making a part like this. And this is a rocket nozzle part that we make out of DD process. So what I'm going to do is give you a little bit details how additive manufacturing works, how the digital design file look like. That's where the attack can happen, and different kind of attack surface and threat analysis for that, and to some extent quality assurance related to this aspect. So before I go into the details, let me talk a little bit about what are the different additive manufacturing technology out there. I mean, you don't need to know all of them, but I just want to give you a brief intro on that. So the first thing I'd like to look at this slide, look at the materials. So you can do from plastic, metal, composite, ceramics. So all these different sort of materials we can actually do additive manufacturing on. Okay. So I'll start from the right, which is over here. On the top right, so it's called material extrusion. So the 3D printer you might have in your home, that's the extrusion type. So you basically have a nozzle, you have a filament coming in, the filament melts, and it deposited the material, you print a part, right? That's the simple material extrusion. Then the second one, we call it sheet lamination. So basically you have composite panel, you have one panel, you basically put something, and then put the second panel, put something, put the third panel, and you stack them together. So that's called sheet lamination process. Directed energy deposition is basically you apply some heat or thermal energy to melt something and create a part. Okay, so the one that I showed in the earlier slide, the video, that's a directed energy deposition process. There is also a powder bed fusion process where you don't work with the material into solid form. You start with a powder form, then you heat it with a laser or an electron beam to melt it and create a shape. So that's what we call powder bed fusion. Binder jetting is where you basically take some liquid bonding agent, and then you spray it, and then you put the next layer, you spray it, and you spray some powder, and you put the next layer. So that's how you process it. That's called binder jetting. And the one before that is wet photopolymerization. So if your printer, home printer, doesn't use a filament, or you don't need to buy a filament, rather you need to buy some resin. Do any of you buy resin for your 3D printer? No? Okay, so there is another type of printer which is also cheap, maybe $5,000. So in that one, you don't buy filament, you buy resin instead. And the way it works, you put the resin, you put a light, that light cured the polymer, then you put the next layer. So that's what we call stereolithography or wet polymerization process. And the last one here is material jetting. So basically you put some droplet of material selectively at different location and you make a part out of it. So this is the whole different landscape and different material system that you can print out of additive manufacturing. But you don't need to know about all these details of this process. What you would be interested in is how this additive manufacturing works and what are the cyber aspect of it, right? So what you are seeing here is a rocket nozzle. It's basically a diffuser, and the process starts with a CAD design. So someone has to design the part, right? So we use a computer-aided design tool, for example, SolidWorks, AutoCAD, this kind of tool to make a part. After you make a part, then you take the part and put it with the or export it in the STL format over here. Then you take this STL file and put it to a slicing software. There are different kinds of slicing software. I'm sure if you use 3D printer, you have used one of them. So Ultimaker is one, Cura is one, Prusa is one. Depending on what printer you are using, they actually comes with a slicer. So you'll have access to that slicer. And what this slicer will do, it will give you a G code. So it will take that 3D part, it will break it down into many layers, depending on how thick is your layer, and it will create a code like this. And you can see this code, it's kind of a machine code where it tells like, okay, do this, do that. I mean, these are the different code and what this means, right? So for example, M140, it means set bed temperature to certain number. And then this G1, you can see this X10, Y-3, that is the physical location of the printer. That's the nozzle is going to go at that particular location. And it executes this as one step at a time, okay? So that's basically the G code that you generate out of this slicing software, and then you pass it to the machine. So before I go to the next step, I would like to say here, this is a very simple, I mean, you can open a G code yourself, and it's just a text file, nothing else, okay? And then you transfer it to your machine firmware, and then your machine will take it to the controller sensor, let's say the nozzle. You set some certain temperature to melt the material, and the nozzle will get heated to that certain temperature and will start printing. So that's why this printing process will happen. And then finally, you will get the part and you can look at the part quality and so on. So this is how the process works, okay? And that's what we call additive manufacturing. We are doing it layer by layer. Now, I showed you many different processes. All of the process more or less looks similar. You start with a G code, you start with a 3D file, then you convert the G code, and then you pass it to the machine, and the machine will take care of the rest, okay? So now, each of these stages that I showed is basically a potential attack surface. And I'll explain how and why. So if you want to look at this, there is basically 3 different layers. So the first layer is a software layer. So in the software layer, for example, I'll give you the example. So let's say you want to create a STL file, and then you want to create a G code out of that. And there is some software that is doing that for you. So you gave a command, okay, make this part, create the STL file. So let's say some attacker attacked that file and then maliciously change the command that you want to do. So they can do it through the software, let's say the Cura or Ultimaker, whatever slicer software you are using. They can have access to that and they can actually alter the file. That will lead to a very disastrous print on your end. So that's basically the software layer. Now on the network layer, let's say after you design that part in your computer, you are going to pass it to your printer, just like you do for the regular printing. You have a file, then you send it to the printer prints it, you collect it, right? Same for 3D printing, right? You have a file that you created the G code through a slicer, then you pass that G code to the machine, and the machine print itself, right? So between this, from your computer to the machine, an attacker can bypass that and basically can give you a very completely different G code that can lead to a different outcome, okay? So that is another layer, which is the network layer. So in the network layer level, they can also attack you and they can also modify the things. Lastly, the physical layer. So the physical layer would be, okay, now let's say even everything is good, but someone can, one of the key idea or key area for this additive manufacturing or this kind of design is the intellectual property. So whatever part you are making, maybe you have a patent on it, okay? So let's say you trying to print in a printer, someone just had a microphone near the printer and it just listened to the sounds during the printing. And based on that sound, it can reproduce the whole part. How about that? So that is basically the physical layer, okay? So it's not necessarily only coming from the printer. You can also leak the data unintentionally, and that can lead to some sort of attack on your system. So that's the physical layer part of it that can be very detrimental. So I'll now give you a little bit more into this different attack surface and how it will look like from the M aspect. So the first one is the IP theft and the design leakage. So I just explained you this particular one. So this is the target machine that you are printing something. So some attacker will probably have intentionally put some acoustic device or may have access to your phone, and your phone record the audio data during the printing, okay? And he basically take that information and then train a model. It recreate this G-code reconstruction, and then you basically get the whole part out of it. So you can get the whole IP theft thing just doing this kind of activities, okay? And the key insight here is that unlike software IP theft, the AM IP theft will directly give them access to the physical part, and there is no reverse engineering more needed for that. You can just recreate the whole thing. Now, for general purpose, like what you have done, probably that's not detrimental, but think from the Army perspective or from the defense perspective, how critical that can be, right? Okay, so the second one is the hidden defect injection. So what will happen is that you have the file, you created the G-code, the attacker take that G-code, modified it somehow, and your print looked very normal. I mean, there is nothing wrong with your print. And then you basically end up with a defective part, okay? So I'm showing it here. I actually wanted to bring two samples. So you can see for this piece and this piece, you can probably see some fluctuation in the dimension, but I had exactly two samples. One is like 100% in fill, one is like 20% in fill. I mean, visually, they will look very similar. But if you take it in your hand, you can easily say, okay, one piece is heavier than other. So something is wrong with the other piece, right? So what they did in this particular paper to look at this aspect, so they actually put some internal infill density by 20%. So that's basically making the material more light and basically removing material. And that actually, if you print the part, it will look very similar. So there is no way you can tell this part is compromised. And then they put it into a quadcopter UAV body, and that actually fell in the mid-flight, right? So there is no external indication of tempering in this piece, but this actually failed due to this kind of malicious attack, okay? So you can see that just changing the G-code and changing just simple instruction over there, you can have a catastrophic event for this kind of situation, right? The threat 3 here is the firmware and embedded system attack. So the tool you are seeing here, so you actually have different kind of firmware in the 3D printer that actually controls all these different kind of physical function. For example, the motor, heater, fan, all this physical process. So the one I'm showing here right here is one software called Octoprint, and they have a web interface. So the goal, I mean, this is an open source tool. The reason they made it, like when we print it, we want to monitor the process, right? So we want to see how much temperature is having, how good is the printing happening. So you can basically do everything. And one of the undergrad in my lab right now is trying to set up this Octoprint system for our printer. And the reason I'm telling you that, I was trying to set up our printer with the IT, with the network at WSU, but our IT system doesn't allow me to. Now I understand why they are not allowing me to do that. So what happened that once you create this kind of user interface with this kind of tools, then you basically expose your system. And once you expose your system, I mean, if you just search HTTP Octoprint, you will see thousands of instances where they're kind of open right now. You can basically attack them if you want, right? So these tools are good. I mean, we need this kind of tool to monitor our process, like what's going on in our printing, but sometimes that can be backfiring us in different way. So one thing can happen, maybe someone attack your system, let's say this printing PTFE, which is a polymer that can held up to 250 degrees centigrade, and he intentionally put your system to 300 degrees centigrade. What will happen? Any idea? PTFE will catch fire on 300 degrees centigrade, and it can destroy your whole lab, and even you can target a building just doing this, right? So you can see the consequences that can happen for this kind of system. So if you have this firmware compromise somehow, you basically have complete physical, have complete physical control of your printer, and they can do whatever they want. So if you're using this kind of tool, be careful. That is the summary here. The threat 4 here is the network level attack. So it basically happens after you get this slicing done, you are trying to transfer to the printer. That's where somewhere is trying to put some changes in your file. So that can happen. And this is one of the example you can see here. So this is the normal print, but after attack, it basically put the nozzle a little bit down, and it basically destroyed the part it is printing. Okay. So that's more or less different kind of threat. I mean, there are many more, but I just give you a brief idea how you can attack a additive manufacturing system to take control or to destroy the part you are making or make a catastrophe out of it. So one of the idea that you can actually use is use some quality assurance as a security control. Okay. So just as I mentioned, like you can first of all visually see if what you are printing is the right piece or not, or if it looks at least visually correct, right? So that's the visual inspection method. You can do some dimensional inspection. For example, you can check out the shape, internal, but it will not tell you the internal strength of it. You can do CT scanning, like you can see the hidden voids inside the part that you made, but it is going to be very expensive. So if you want to do a part like this, maybe it will cost you $1,000, and then it will also cost you time for doing that. You can also do some other sensing. For example, ultrasonic is one, which is very useful. And you can also do some destructive testing. For example, you can put it in a tensile testing machine or some hardness testing machine to see if the part has the strength that it is for, right? But these are destructive testing. So once you do that, your part is destroyed, right? So the key question is, can a compromised part look correct, pass the basic checks, like just the visual checks, and still fail in use? The answer is yes, it can. And that's where my personal research is. So my group is actually looking at this different kind of process monitoring. So we don't want to wait for post printing part. We are going to print it. We are going to inspect it during the printing, just collecting data, maybe some ultrasonic sensor, maybe some acoustic sensor, thermal sensor, and then use some machine learning tool to determine or detect like if there is any defect happening in real time, right? And if there is also an anomaly happening, and obviously we are not looking into the cyber aspect, but we can also consider that, like if there is any cyber issues that can lead to those kind of event or not. I mean, for now, we are assuming there is no cyber manipulation. It's just the process happening and the quality assurance of that, okay? So if I want to secure this AM workflow, what should I do, right? That is the next question. And in the IT manufacturing community, we have think it through a little bit. So one idea is that, okay, once you have the design file, you will create some hash and also signature for the digital part. And then you use some secure transfer protocol. And then on the machine side, you will verify that signature, right? If that is coming from an authorized person or not. And then you authorize the print, and then you print the part. So in terms of the defensive mechanism, these are different technique has been proposed. I'm sure you know more about that. I don't need to explain all this for now. So I'm skipping this part, but the idea here is that you are going to create a design file, you are going to create a digital signature, and that has to be authorized, right? If you can do that, then probably you can secure the system. So what I want to show here is that STRIDE framework. Are you familiar with this framework? Okay, so this is a common framework for cyber physical manufacturing workflow. So I'm going to explain a little bit and what would be the corresponding AM example of that, right? So the first one is spoofing. where you can think of for the M example aspect, a fake designer submits a print job. So what does a fake designer means is basically someone is trying to send you a file, right, who is not the authorized person there. Then you can do tempering. So basically you are tempering the G code that I already talked about. The repudiation is there is no audit trial for who changed the file. So that's why that having the digital signature and having all this trail for like who is doing what in the process, that will be very helpful. And then information disclosure. So like I mentioned, the data leakage, just having a microphone just beside the printer can also have this kind of consequences. So you can have this kind of information disclosure. Denial of services. So you can have maybe someone attack your printer. He made like 1,000 print without your authorization. So that would be something like flooded. And you can also log the printer somehow if he has access to. And then elevation of privilege is basically he will exploit whatever way he can to your printer system. So this is the kind of analogy between the CS domain and the AM domain, like how these two threat modeling can happen. So that's actually end my part of additive manufacturing, right? So now I'll give you a little bit more onto the other advanced manufacturing domain and what kind of threat we are seeing there. So I have like 20 more minutes. So I'll be trying to go a little bit faster on this aspect. But if you have question, you can ask me later. So the first one is the CNC machine, which is the most similar to what we have just seen, the additive manufacturing process. In the CNC machine, we also have the G code. You also create that G code, send it to the file, and then send it to the machine, and then you print it, right? So the consequence is that a CNC machine can cost up to 500K to 5 million. And even if you just change it, let's say you increase the power or the speed of the tool, it can actually break the whole thing. You can basically lose your $5 million machines, right? So it's very important that whatever G code you are printing has to be verified, right? On the robotic side of it, you have a robot operating system that called ROS, and that robot operating system actually controls these different robot joints and others, right? So if you have seen robot, for industrial robots, these have very high payload. For example, KUKA or some, let's say Phonak, they can have payload as good as up to 1,000 kilogram, okay? So that's a huge payload. And if someone can hack your robot, they can actually change the position of this different motor over here, and that can lead to different kind of disaster. It's not only just a concern of your part you are making, it's also a security and safety concern. Like it can, probably you can use it to kill someone. It's very possible to do that kind of thing, okay? So this is another aspect. The digital twin aspect is that, as I mentioned earlier, you have to have a physical twin, and then you also have a digital twin. And the main aspect here is that whatever happening in your physical twin, let's say this is a rocket engine, you are collecting some real-time sensing data, maybe the temperature of the inlet airflow, the temperature of the outlet gas, the blade temperature, and all these sort of things. It has to be transferred to the digital twin to kind of come up with a predictive modeling, okay? And then you pass it back to the physical twin to take the next action. Now, how attacker can manipulate that? They can actually make it slow. So it's not real-time update, okay? And if this is not real-time update, that can lead to different consequences, right? They can also take that feedback loop into account, and then they can exploit it, okay? So that is also a very important aspect of it. And then they can intentionally damage this data connection system. So your digital twin, whatever it's predicting, it's completely garbage. And that leads to maybe a failure of a plane. You can take control of a plane if you have a digital twin of that, and you can basically destroy it. You don't need to throw a bomb or something like that. You can just manipulate that system to do that. Because you know from the, all of you have flight, so for plane, most of the system are automated. There are little human input. Like most of the time you fly on autopilot. So if someone take control of that, what will happen? And this is one way to take control of that. You can take the digital twin inside that running that engine and destroy it. So one key aspect is that the data that we are collecting from the physical twin and passing back to the digital twin to physical twin. So the digital twin will be as good as the data quality, right? So the key aspect here is that if you can manipulate the data, you can manipulate the digital twin. So that's very important, okay? The last one here is the smart factories and IoT security. So as I mentioned earlier, nowadays now you have many machines, and these machines are not isolated. They have some networking tool that basically communicate with each other. For example, you can see here a car manufacturing system. So it comes from different kind of supplier. I didn't talk about the supply chain as well, but that is also another aspect of manufacturing. So let's say some supplier gives you the tire. There is some robot that putting that into the car, and then it goes through all these different cycles. So you can manipulate that in one of the aspect. Let's say you need 50 tires, but you probably your inventory said, okay, I need only 20. So what will happen? You will wait for the 30 to come in, and that basically leads to some economic consequence, right? So the key idea here is that all this machine that is kind of interconnected now. So that's where is one of the possible cyber attack surface, okay? So if I now take all these different advanced manufacturing technique and kind of try to put some consequence and detectability. So this is like how the landscape look like right now. So additive manufacturing is the consequence you can see critical and detectability is very low. This is because additive manufacturing is something we started very recently. As I started, like some of the manufacturing technologies are old, like old and old and old, right? But for additive manufacturing, this is there for last 10, 15 years. I mean, it has to be more than that, but mainly the manufacturing is getting the traction for last 10, 15 years. So we still have a lot of things that we don't know. We still have a lot of things that we don't control. I mean, we have to have an attack before we do something about that, right? So we're still exploring this aspect, and this is kind of the novel aspect of it. Like we don't know many of the additive manufacturing side of it. CNC machine has been there for long, so you can see the consequences are high, but still the detectability is low. Like if you have this kind of cyber attacks, there are a lot of ways that you can do cyber attacks on those kind of systems. Industrial robot, digital twin are all kind of, the consequences will be very high if you can hack some of those systems, right? So I talked about different kind of attack and for additive to advanced manufacturing. Now let's take a look quickly what are the defensive framework that people have been developing. So one of the key area I think for in this area is developing by NIST. So NIST have this operational technology security protocol, NIST SP 882. So they are actually giving some guidelines like how to set it up for this kind of manufacturing system. And this is a international guideline, international protocol right now, IC 62443. I'm not going into the details, but if you're interested, you can search this name and you'll be finding the detail. The most interesting one is this, and I recommend if you're interested in additive manufacturing to read this one. So this is coming from NIST AM Cybersecurity Roadmap. They published a roadmap on 2023. And then also NIST has other CSF 2.0, other cybersecurity reports. So right now the framework looks like this. So they first govern, identify, protect, detect, respond, and recover. So that is the cycle they actually use. So, I mean, there are these different cybersecurity tools, but now the goal here is not just, okay, I want to ensure one of this. It has to be kind of integrated with the manufacturing system. So this is one of the model that I want to share with you. So this is called Purdue model, and you can see this different level. And if you look up to this is up to OT, operational technology, and after that, this is IT. So level 0 is the physical process, where your sensor, actuator, machines, these are working. Then you go to level 1, where you have basic control like your PLC, your controller, all this will come into the picture. Then level 2 is supervisory control, where you have SCADA or human machine interface, those kind of things. Level 3 is the manufacturing operation like workstation, IO server. And this 3.5 is the one where is most important thing will happen. So this is what we call demilitarized zone, DMZ. So for this one, you basically have connection with the IT, and level 4 is the enterprise network where you have web server, email server, DNS server, and level 5 is corporate IT and others, right? So some of the event that happened, they actually got access to that level 4, and somehow they could penetrate through all these different levels, okay? So that's why this demilitarized zone is designed so that you can make sure a attacker who is coming from this IT cannot reach to OT. But still, there are a lot of vulnerabilities. I mean, there are a lot of situations that has not been taken into proper account. So that's the research aspect of this particular field that's going forward. I'll skip this particular one. So it's basically how you secure development for AM software and firmware. And then the anomaly detection aspect. So you can look at the process signal. So basically you can have your printer, CNC robot, whatever you are using. You can use different kind of sensing tool. Then you can use a machine learning model that can give you alert in real time if there is something happening, right? So you can, I mean, that can be an interesting research direction to look at. You can also look at the network signal. So it's not only just looking at the printed part. You can also look at if the protocol is correct, if the behavior model is correct, if there is any suspicious activity happening. So you can also look into the network signal to see these kind of things. So the key challenge here is that the false positive rates in the manufacturing sector has to be very low, okay? If not, then you can, if you just give a false alarm, like, okay, something is happening, and if that is false, it can lead you to $10,000 to $1 million per hour, depending on what industry we're talking about, okay? So that's why this is important. It's not just, okay, I identified everything, right? You have to be very careful when you say something like that as an engineer. So research frontier, I'll just briefly talk about what are the research going forward people are looking at in this field. So one of the key idea is that how we can detect this hidden sabotage, right? So I have the part, it looks very nice to me, everything looks fine, but inside it, there is a defect that someone maliciously input that, right? So how we can detect that? So one idea can be we can monitor it in real time. So we don't only rely on, okay, it's just the visual inspection. We also rely on the external sensing to see what's going on. We can look at different kind of lightweight security tools, like you can put some encryption with all those design files, right? And how that can be used. So I think there was a competition from NIST back in 2023. So they actually came up with an idea, it's called NSA competition. So 8-bit to 32-bit encryption. And the thing is that the idea is there, but it has to be replicated for thousand, millions of machines and has to be done. I think that part has not been done yet. Quality inspection, as I said, like you can use ML tool now to detect those kind of things or give you early alarm on that. Secure design collaboration, like it not only design the part, you also want to design the part and have the IP things to be ensured, and how you can do that, that is one of the key aspect. Forensics without shutdown, you don't want to shut down the system. You also want to look at if something is happening. So without shutdown, can you do some forensics, what's going on? And trusted AM provenance, like can we track the every aspect of the design and kind of create a pipeline so we can ensure only the authorized person is able to print, okay? So these are some regulation right now. So EU has this Cyber Resilience Act. There is also, they're mostly for network products. Then there is also CMMC 2.0 that's basically incorporated in DoD contracts. Like if you're doing any DoD contracts right now, you have to make sure that you pass that regulation. FDA medical cybersecurity guidance, there is also one for the medical related manufacturing. Then also you have critical infrastructure manufacturing. There is also some guideline on that. So, I mean, I'm giving you a whole overview of this sector, and this is not obviously very detailed on each of them. But you can use this as kind of a tool to go into deeper and then see what others it has to offer. So this is kind of the summary. I'll not read it through. Just the key takeaway here is that cybersecurity in manufacturing is not optional. Engineers and future leaders have to integrate this security into the manufacturing system. This is very critical, very crucial, not only from manufacturing point of view, but also from national security point of view. Okay. With that, I'll end my talk and I would welcome any of your questions.
Hi, my name's Morgan. I just had a question about your research. You said it was mainly for additive manufacturing, correct? Like while something is being printed, you're in real time checking. Could that be like translated into other manufacturing, other parts of the industry, like, for example, CNC machining and like more sensitive parts, like you mentioned Stuxnet, so
Yes.
uranium enrichment. Could your research be utilized in those fields as well, or?
Yes, that's a great question. So what we're doing in my lab, so we have a wire arc additive manufacturing system. Have you seen welder? Have you done welding at some point of your life? Okay, so you're using the welder with a robot, and that welder is depositing material layer by layer, and you are making a part, right? So the sensing system we're using with that wire arc system is a microphone, just listening to it when it is printing. We also have a IR camera, which can go up to 2200 degrees centigrade. So you can think of this as very, very hot, right? And we also have some optical camera and thermal camera just to look at what's happening. So these are the three sensing modalities we are using right now. Now, how we are using these modalities? We cannot use just those sensing data in raw format. It's not just that useful, right? So we're using different kind of mechanistic feature extraction technique to extract different feature, and then we are training a machine learning model. So the very recent work we did on agentic AI framework. So we have two agent. One agent is just looking at the welding signal that comes from the welder. Another agent is looking at the monitoring signal that coming from those acoustic, thermal, all these different kind of sensing. And then the machine learning model take decision. What kind of decision? Like if there is a defect forming or not. So one agent might say, okay, I feel like there might be a defect. Then I have another modality to kind of confirm that, yes, there is a defect forming, right? So now your question about transferability of this real-time in situ monitoring to other manufacturing, the answer is yes. You can do it for other manufacturing system as well, especially for metal additive manufacturing, that is very critical. And it's not only critical because you want to monitor it. For example, let's say there is a mission from Army or DoD that's in remote Afghanistan. You don't have CT scan tool there, but you can easily have a audio or a microphone there. And if that audio microphone can tell you how the quality of that part is that part is safe to fly with your bomber, that actually helps, right? So people has been using it for metal additive manufacturing. For polymer, yes, we have this kind of sensing, but I don't think polymer is going to be very critical because those are cheap kind of thing. Like you can make one part maybe in a few bucks. But for metal part, it's going to cost you maybe more than $10,000 to make a part, right? So that's where the value is. And those industries like aerospace and biomedical, those industries are adopting metal additive manufacturing. So they are very safety critical, very important field to look at. So yes, so the summary is that yes, this kind of sensing using machine learning, because the data when it's coming into huge volume. So I can give you one example. If I run my machine for 30 minutes, it will create you 2 terabytes of data. As a human, can you monitor all this to say what's happening? So that's where the machine learning is helping us. So it's looking into the data into real time, and it's giving us signal. Okay, something is happening, something is wrong, take care of it. So that is one aspect. The next aspect is, okay, I sense it, like there is something happening. How you can rectify it in the next layer as you are printing. So that aspect is also there with that monitoring. Does that answer your question?
Yeah, that was very cool. Thank you.
Thank you.
We have time for one.
All right, thank you. So earlier in the slides, you mentioned that like an adversary could capture like the acoustic signals from one of these like CNC machines or printers and rebuild the G code. How do you like what are mechanisms to prevent that like from occurring from someone capturing those signals when like you can just have like a pocket microphone on you? Would you want to like I don't know, like create like false signals to trick them? Like what are your thoughts?
Yes, so yes, there is really no great mechanism to prevent that kind of attack, right? So, I mean, I can secure the printer, maybe I can secure the network related to that printer, but let's say someone hacked your phone and you were there when it's printing or it's doing that CNC operation. So there is probably, I don't know, there might be way, but from my understanding, there is not a good way to handle all this kind of threat that we have.
All right, thank you.
Excellent. I wish that we had time. I really enjoyed it. It was a wonderful, wonderful overview of the area you work in. And I'm going to encourage those of you CySER students who haven't picked up a project yet when the spring semester next year comes. This might be an area, and Jade would be glad to have some of the things that he's talked about, a more concrete one that can be done in a semester along with the graduate student and so on. So I really strongly encourage you to think about that and apply what you learn in cybersecurity to an interesting area. So thank you very much for a very nice job, and the slides will be up so you can review them later on. You're welcome to stay. We have another session. There's coffee, I hope. We'll take a 2-minute, very, very quick break because the next speaker is going to be online and we don't want to be late for that. So just 2 quick